Welcome to this video. Last time we saw what the structures are in the eye and how they work together for vision. Here, we're going to look at the different types of vision. And in fact, as it turns out, there are two different types of vision based on the two different types of photoreceptors that the eye has. So the retina, that back layer on the back wall, has cones and rods. Rods are responsible for what we call scotopic vision. That's when we detect motion, when we see in black and white, when we see in low intensity light, so at nighttime or when you're looking in your closet. And they are responsible also for peripheral vision. So peripheral vision and motion kind of go together. If you're walking along, it's nighttime, and you're back in the olden days. Your great 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 grandfather is walking through the woods. It's nighttime, and he's afraid of tigers coming out, right, and eating him. So his scotopic vision is detecting motion in the bushes on the periphery. So out on the outskirts of his vision, he's looking straight ahead, but he might think he sees something rustling in the side, on the side off to the right. His peripheral vision is detecting motion. Those are the rods working. Rods don't distinguish color. They really just see in black and white. And they don't see fine details. They're after just the motion, general motion. On the other hand, there is a different type of vision that we have. It's called photopic vision, and it's the vision that the cones provide, or it's the vision that uses cones. So this is easy to remember. Cones see color. Right? You've got a little alliteration there. So cones distinguish colors. They see fine details. They see little objects really clearly and very acute, with great acuity. And they do see in high intensity light. So these are the two different types of vision. One comes from rods, the other comes from cones. Cones see color, and rods see the rest. Okay, you might be wondering, where are cones and rods in that retinal layer? I mean, are they just evenly spread out? The answer is no. You don't just get a bunch of cones and rods evenly, distributed across the retina. That's not true. We're going to take the fovea as kind of our reference point. If you're 0 degrees away from the fovea, right at the fovea, there are tons of cones and no rods. If you go 10 degrees away from the fovea, the number of cones has dropped dramatically, and the number of rods has increased. When you get to 20 degrees away from the fovea, you have almost no cones left at all. And what's kicking in? It's your rods. And as you increase farther and farther away, you have really just rods operating. And that makes sense because rods are responsible for peripheral vision. So if there's something kind of off here to the side, below, you're not looking at something on the ground, you're looking straight ahead, but there's some object, a frog down here. That frog is going to be detected over here, and that's part of your peripheral vision. So it's the rods, the rest, not the cones, not the color, but the rods that allow us to see that frog in our periphery. Okay, so there's a chart that we use for showing the distribution. The x-axis is the angular displacement from the fovea in degrees. It's how far away we've gone. The y-axis is the density. So when we are at the fovea, 0 degrees away, there are tons of cones and no rods at all. The rods is like 0. As we go away, as we go farther to the left, so down in this area, negative angular displacement, and to the right, positive angular displacement, the number of cones drops dramatically, and the rods increases rapidly. So right here at 20 degrees, that's where negative 20 and positive 20, that's where there are a maximum of rods and no cones at all. So I'm going to ask you on the homework to kind of explain in your own words the density of rods and cones relative to the fovea. And you'll just have to put this graph into your own words. Now, Cones and rods, as it turns out, do not respond equally to every single wavelength. In fact, we know that there are certain wavelengths we cannot see at all. We can't see infrared, we can't see ultraviolet. Those things are invisible to us visually. So it's no surprise that certain colors are more heavily detected than other colors, just because, in general, the eye is really good at seeing particular wavelengths, and it can't see other wavelengths. So rods are more responsive to around 500 nanometers, those wavelengths. That's where they peak. And cones are more responsive in this area. Now, as it turns out, rods have only one type, but cones have three types. So this is like the combination. This is the combo of all three cones. Let's look at the three types of cones. Or in other words, this is like the combined effect, the combined sensitivity for all of the cones together. So we said that rods have just one type, but there are three types of cones. The types of cones are broken by color. They're classified according to color. There are blue cones, green cones, and red cones. And the blue cones see, or they respond to these wavelengths. The green cones respond from, wow, look at that. Green responds to blue light. So there's overlap. And it even responds to a lot of red light too. The red cones respond to these wavelengths. But here's why we call this one a blue cone. It's most responsive, it absorbs most, the y-axis is absorption, it most absorbs blue light, 450 nanometers, or 445. The next cone, the green cone, is most responsive, it most absorbs green light, 535 nanometers. And red cones most heavily absorb 575 nanometers, which is red light. Now, you're probably wondering how the two graphs I've shown you fit together. The graph from the last page, this one here, in fact, blue cones, green cones, and red cones do not absorb the same amount of light. Green cones absorb more light than blue or red. So if we scale that appropriately, here's what the picture actually looks like. This is a more accurate representation. We don't need to know this for IB, but I just want to make sure that the two pictures come together clearly in your mind. Blue cones absorb the least amount of light of the three. Green cones absorb the most, and red cones absorb the middle amount. Now, blue cones are called S cones because they absorb small wavelengths. See how these are smaller numbers? 400 is less than 500, which is less than 600. So these absorb small wavelengths. Green cones absorb middle wavelengths or medium wavelengths, so they're called M cones. And red cones absorb red light, which are long wavelengths. So those are called L cones. If you combine the three graphs together, the combined effect is this dotted black line here. And that dotted black line is what you see right here on the left graph. So the cones, all three cones combined together, still absorb less light than the rods. Does that make sense? Should the cones absorb less light than rods on the whole? The answer is yes, it makes sense. There are far fewer cones than there are rods. That's what this graph shows. You really only have cones in the first positive 20 to negative 20 degrees. That's the only place where you have cones. And then there are rods covering all of this extra space here on the top and bottom, up there and down here. So there are far more rods than cones, and that's the reason why the rods absorb more light than the cones absorb on the whole. And of the cones, the ones that absorb most light are M cones, or the green cones. Okay, the last thing in this video is color blindness. Really simple, really straightforward. Color blindness, as you probably know, is when we can't distinguish pairs of colors. So some people are red-green colorblind. They can't tell which color is which. The causes include faults in how the cones develop, but damage to the eye or brain can cause it as well. and so can damage to the optical nerves. So red-green color blindness is the most common. It's genetically inherited. So there's this fault in how the cones develop. The fault exists because of a genetic abnormality, and that genetic abnormality is passed on through the genes from generation to generation. And faults in the cone development is the only one we have to know for IB. So that covers it for this video.